let's continue. We need to figure out what the angular momentum eigenstates are doing. Okay, and that doesn't necessarily mean we need to know their explicit form. You may remember some of their explicit forms from the solution of the hydrogen atom. That's not what I'm going to worry about. What I want to know is what does the eigenspectrum looks like. Okay? So what we already know is that the eigenspectrum is described by good quantum numbers of two operators, j square and jz. I could have taken jx and jy or jy. I've chosen, made a choice. I've chosen jz. Okay? And furthermore, I'm going to start by assuming that j square acting on some state psi gives me the eigenvalue alpha, and jz acting on the same state psi gives me the eigenvalue beta. So that's where I'm starting from. Okay, so quick recap of where we were yesterday. And I assume that the raising operator acting on that state psi takes me to some other eigenstate of j square and jz. I call that phi. Okay. So what we want to know is what happens when j square acts on that state phi and jz also acts on that phi. Okay. So in order to do that, I needed to make use of the fact that j square commutes with j plus and j minus, and because it commutes, it's very easy to show that the eigenvalue of j square does not change under the action of j plus. Actually, it's true even of j minus. Okay? The eigenvalue alpha, whatever it is, refuses to change under the action of these raising or lowering operators. But that's not true of, as it turns out, that's not true of jz. And the reason is straightforward. Jz does not commute with j plus and j minus. J square did, but jz doesn't. So therefore, there's no reason to expect that this eigenvalue beta, that's going to remain unchanged. Okay? And indeed, with a little bit of maths, you can first of all show that jz commutation with j plus again gives you back j plus with a factor of h bar, and jz with j minus gives you j minus but with a factor of minus h bar. Okay? So this tells us that indeed these operators, raising and lowering operators, do not commute with jz. So as a consequence of that, when you ask what happens when jz hits phi, the new state, which was reached by the action of this raising operator, you can use the commutation relations, okay, and you can show that this actually increases the eigenvalue by an amount h bar. And as I pointed out, h bar is the most reasonable thing that you could have obtained from this action. There's no reason that it would have been h bar square or something else. Those would not have even been dimensionally correct. Okay? So that means that, so this is why this is called a raising operator. It increases the eigenvalue of the jz. Okay? So one way to picturize this, as we will see later on, is essentially that what jz is doing is, if you have the j, classically if you think of it as a vector here, j plus is just increasing it this way. Okay? It's just raising the vector such that its z component will obviously increase. Alright. Now, as someone asked in yesterday's class, can we actually keep doing this forever? That doesn't even make sense. Okay. In fact, somewhat like the harmonic oscillator, this spectrum has to be bounded from below. And unlike the case of the harmonic oscillator, this spectrum must be bounded from above as well. Because even on classical grounds, the z component of a vector can never exceed the norm of the vector. Okay? So therefore, there must be an upper bound and a lower bound. So what that means is that if j plus acts on some state, let's call it psi max. If it acts on that state, if it tries to raise it further from there, it must annihilate it. This was not even true in the harmonic oscillator, where the spectrum just kept going to infinity. That was not forbidden. Similar to the harmonic oscillator, there must also be a psi min, such that if the lowering operator hits that guy, it can take you no further. Okay. So both these constraints must come into play. Now, in order to see what we can do with these constraints, right? So the way to do it is, the way to implement it is as follows. So it's important to note that the operator j square can be represented in terms of the raising and lowering operators, okay? But it's not terribly straightforward. It's not just a simple sum of j plus and j minus. It's actually product of the two. Okay, so there is either a j minus j plus or a j plus j minus that comes. And you also need jz and jz square in the game. Okay, so j square is not simply a function of j plus and j minus. Okay, it's not some simple function of just these two. You also need jz in there. Now, how does this come about? Okay, so the algebra is actually reasonably simple. Look at the product of j plus and j minus. That's written as jx plus ijy into jx minus ijy. Open up these brackets, alright? And remember that ordering matters. This is quantum mechanics. These are operators. You cannot assume that they commute. Okay, so the cross terms, don't write it as 2 times something. That would be naive and stupid. Okay, so the cross terms indeed give rise to a commutator. And we know that in this case, the commutator of jx and jy will give rise to ih bar jz. And that's how you get this h bar jz sitting out. The other two terms are just jx square and jy square. My bad, this should have been this thing. Jx should have been down here. Okay. Alright, so what we can see is that jx square plus jy square can be written as j plus j minus minus h bar jz. Okay. In the same way, you can also do the maths and show that j minus j plus can also be written as jx square plus jy square minus h bar jz. Okay. So then, this relationship where j square is equal to jx square plus jy square plus jz square, now this becomes trivial because what we've obtained is an expression for this fellow down here. That's what we've got here. These two expressions. Okay. So the square of the x and y components is actually related to the plus minus operators, the raising loading operators, the product, as well as jz. Alright. So now we can use this guy. So let's look at what happens, okay, when j square acts on psi max. So that should give me alpha, that has to give me alpha. That's clear. But j square acting on psi max is basically, I can write it as j minus j plus jz square plus h bar jz. That I've just obtained. Okay. Now the first term, because look at the way that object, the first term will act on psi max. It's j minus j plus acting on psi max, which means that first j plus acts on psi max. But as soon as that guy acts, by definition I annihilate. So therefore the 0 obtains. Okay, so that's how this 0 comes about. So therefore that object on this state has no action. But the other two are just beta max square and h bar beta max. Yes. Sorry? No, j squares by definition was alpha. J square's definition was alpha. That's all right. So what we can see here is that alpha is a simple function of beta max square plus h bar beta max. We can play the same game with j square acting on psi min as well. Okay, and there I will purposely choose to represent it using the other relation. I'll use j plus j minus in its place, such that again that term will annihilate psi min and give me a 0. And instead what I'll end up with is this relation. Alpha is also equal to beta min square minus h bar beta. So note I've got two nice algebraic relations. Alpha is related to both the upper bound, beta max. It's also related to the lower bound, beta min. Okay. So the spectrum of Jz, somehow the upper and the lower bounds of Jz spectrum is tagged with alpha. So then it's very simple. What we do is, since alpha is equal to both these quantities, right, just equate them to one another. When you equate them to one another, do a little bit of algebra, okay, write it, take them across, complete squares kind of stuff, and you can show that beta max is actually minus beta min. That makes sense. Guess what? Think classically. What is beta max? It's the largest value of the z component. Okay? Yeah. And what is beta min? The lowest value. But then that should be, classically they should be opposite to one another. Okay? For a vector, that will happen because this vector can rotate now. So when it's absolutely up there, that's beta max. When it's down here, it's beta min. Exactly negative 1. Okay, that does make sense. Yeah?
Also, it does not necessarily mean that that's a consequence of whatever.
But it does make classical sense as well, thank God. Once in a while this happens in quantum mechanics as well, But that classical intuition does come through. I mean, it might seem shocking to you, but it's not just the maths. Certainly there's some physical intuition going on here. Now, this is good to know that beta max is equal to minus beta min. But we also know that the action of these raising operators in a finite number of times must have taken me from beta min to beta max. Because after all, if I start from down here, I apply Jz, this J plus once, it comes here. Then I apply it again, it comes here, and so on and so forth. And there must be a finite number of times before I align completely up. Okay. So therefore, there must be this relation as well, that beta max must be equal to beta min plus n some integer times h bar. Okay. Where n is some integer. Why is it necessary to be finite? If the norm of this vector is finite, then you can easily convince yourself that this sequence will also be finite. Because, think classically again, if the norm becomes infinite, then beta max and beta min will also become infinite, classically. Then in that case, I will need an infinite number of such sequences in order to go all the way from the bottom floor to the top floor of this building. There's nothing outrageous in this. So when I use these two relations together, the fact that beta max must be equal to minus beta min, as well as the fact that they're related to one another through n times h bar, solve the two together and you can convince yourself that beta max is n h bar by 2. Okay. So does that relation look surprising to you? Where n, of course, is some integer. Does this look surprising to you? The fact that the z component can at maximum be n times h bar by 2. No? Doesn't look surprising? Think a little bit. I'm sure you guys watch a lot of videos on YouTube. Why would this look surprising? Okay, so let's unpeel the mathematics. Imagine n is an even integer. Then what is beta max? It must be an integer value. But what if n is odd? It must always be a half integer. Now, where on YouTube have you come across the fact that as against?
As against normal multiple.
No.
As in, like spin half would mean that it's half integer. It would mean that if you rotate.
It'll take you some time to unpack that. You haven't been watching YouTube closely enough, or they haven't been doing a good enough explanation. Turns out the universe is divided into two halves. Okay, there's the force particles and there's the matter particles. Okay, and I'm not saying anything mumbo jumbo Jedi lore from Star Wars here. Okay, this is just experimental fact. All right, we have the matter particles and we have the force particles, and it turns out that the matter particles always have something called spin, and we'll see what that spin is. But that object always comes with half integer values. Okay, and the force particles always come with integer values, the spin of those force particles. So it is quite interesting to see that this is coming out in a very straightforward manner from these simple considerations. We are not doing anything terribly fancy here. We're just asking ourselves that if we want angular momentum eigenstates, what should the spectrum look like? And you immediately reach the conclusion that this spectrum will be bounded in its upper and lower values either by an integer multiple of h bar or a half integer multiple of h bar. You cannot get which you could have obtained in the classical world, you cannot get h bar by 65 or 3.142 times h bar. You cannot get those values. You can either get h bar, 2h bar, 3h bar, etc., or you can get half h bar, 3 halves h bar, 5 halves h bar, etc. So that should be somewhat shocking, right? So if you had not discovered all those particles, and if somebody were to tell this to you, your first reaction should be, what? Why only these guys? Well, experimentally we know that these guys come in for a particular reason.
Can it be non-negative? In this case, since we rejected the idea that V max is lower than V.
Sure. So yeah, it is an integer and n is greater than 0, greater than equal to 0. Okay, so what have we seen here? What we've seen can be succinctly put into these two relations. Okay. Define j, this small j, to be n by 2. Why? We've got n by 2 out here now. So define that. And then you can show that alpha, this eigenvalue alpha, okay, this it turns out is equal to h bar times j into j plus 1. Okay, and beta is equal to some other quantity mj, right, m sub j times h bar, where this mj can run from minus j to plus j, but always in unit increments. So let's take a special case. Let's take j equals to 1, let's take n equals to 1. So therefore j is equal to half. Okay. So for that special case, it's probably the simplest case we can imagine, what would the spectrum of, what would alpha look like? It can only take one value. Alpha must be equal to 3 by 4 h bar square, because it's 3 by 2 into half. Don't forget, it's j into j plus 1. And the other guys, beta, this lies in a range. What is the range? Of just these two values. That's it. Minus h bar by 2, h bar by 2. And it turns out that this is the simplest case of angular momentum that you can get. This is the spin half problem. We will come to this very soon. So this is what we obtained by just looking at this, for instance. So you might have wondered, where did he get j into j plus 1? Okay. Just alpha is this. J square acting on psi is alpha times psi. Alpha is the eigenvalue here. Now take this object. We have alpha is equal to beta max square plus h bar beta max, right? And what did we just see? Beta max was h bar n by 2. Feed it in here. So I take this n by 2 and write it as j. So I write it as j times h bar. Feed it in here and you'll immediately see that you get. Okay. Again, think about this classically and you get a bit of a surprise. Classically, what would you have thought of as the norm of a vector? You would have thought that it would have been j square times h bar square. But note here, it's not just j square. Of course, the dimensional grounds, it would have to be h bar square. So that's okay. But if you would have asked, since I think of j square as the sum of jx square plus jy square plus jz square, okay, then it's not hard to convince yourself that maybe this can be something like the square of some object again, times h bar square. Okay. But it's not. So in the quantum world, there's a small twist there. It's j into j plus 1. Okay. So that extra factor of j is a sign again of the fact that something is different in the quantum world from the classical one. So we're close to our classical considerations, but not quite. Okay. So then this is the spectrum we've ended up with. J square acting on psi gives me h bar square into j plus 1 into psi, and jz acting on this gives me this nj h bar, where nj lies in this interval. So the way to think about it is this picture, is this representation. So this representation is shown for the orbital angular momentum. The same thing will work for total angular momentum as well. So these are these representations of the vector L, that's the arrow shown there. And of course, the length along the z-axis is given in units of h bar. Okay. And if I take a cut, then that is the picture on the right. Okay. If I take a cross section, a vertical cross section. Right. Good. Okay. So what else is there to see now? There's just one last thing that we need to see before we can dive into the world of spin, which is the following. Okay. So what have we seen so far? We have states, psi, angular momentum states that can be written in terms of two good quantum numbers. The two good quantum numbers specify the total, the norm, and the z component. Okay, j and m sub j. By the way, this is something the chemists must have told you about a long time before we did, right? The physics guys. Yes? But if you now think back to the way the chemists were doing it, they typically use rather hand-waving rules. Okay? They say, okay, no, this is the way we seem to find it. Which is okay if you come at it from the experimental point of view. Experimentally, if you're doing spectroscopy, then you see those rules. Alright? But this is the maths that actually leads to those rules. So it's nice to see that there is some strict mathematics that actually unveils all those rules. Because if you really now go back and look at your stuff, whenever the chemist showed this to you, you would have seen that there's a bewildering variety of these rules that they throw at you. When you first sit in their classes, they say, look, this has to be like this, and this has to be like this, and there's an entire tableau of such rules and relations, and your head probably spins. Mine certainly did the first time I came across it. But this is how it's all happening. Okay? Yeah? Oh yeah. Let's do that in an assignment and see where the Klebsch-Gordon series comes from. Coefficients come from. No, we'll come to that. All that stuff happens when we add angular momentum. Okay? But there is, the physicists actually had to do all of this. And the chemists just teach it as if, these are facts. Right? It's more than that. That's what I'm trying to impress you. Okay. So the last thing I want to do is the following. You remember, all of this came out from the fact that I said that, look, these elevator operators, raising and lowering, when they acted on some angular momentum state, they took me to another angular momentum state. Remember? Yeah? So, we said that indeed that this new state phi, okay, this should be proportional to an angular momentum eigenstate. Right? And indeed, if it's a raising operator, if this object was appeared out of a raising, the action of a raising operator, then the mj value should have increased by +1. And if it came out of the action of a lowering operator, then mj, the eigenvalue of the z component, should have lowered by 1. So it should go to mj -1. Again, sensible, right? But are these two states exactly equal to one another, or are they proportional to one another? So which means that when j plus or j minus acts on the state j and j, does it exactly lead to this guy, or are there some coefficients in front? Turns out that there are some coefficients in front. So what are these coefficients? The reason we're going to do this is because these relationships will be useful to us going forward. It turns out that these are the coefficients. Square root of j into j plus 1 minus mj into mj plus minus 1. So in an exam situation, I might want to advise you, it's good to keep this in mind. If you know how to derive this on the spot, good for you. But this might be just one of those things that at least I've found is just good to just store in your head. Okay, because deriving this on the spot will just cost you another few minutes. Alright, so this is one of those few things, relations, that most of us tend to forget. Right, but can be very useful. Let's see where this came from. Let's look at j plus. J plus acting on this is a definition. I say that it's this coefficient times the next state of angular momentum state. Okay? So this is the action of the elevator operator. Good. Now if I take the Hermitian conjugate on both sides, then this guy, right, if I take the Hermitian conjugate, then it corresponds to the action of the Hermitian conjugate j plus dagger acting on the bra. But we know that j plus dagger is actually j minus. So that's the guy acting on the bra. Okay? So by definition, that should give rise to this coefficient, but its complex conjugate, star, times the bra, the raised bra. Good. So now what we'll do is the following. We'll take the product of these two relations. We'll take what happens when J plus acts on this, and we'll see what happens when J minus acts on this, and we'll hit them together. Okay? And we're going to use the fact that J square is J minus J plus H bar Jz plus Jz square. So what I've done is I've taken this relationship and I've taken this relation and I've bunched them together. I've taken the matrix element of these two operators together. Okay. Why? It's because I can use this relation, J square is equal to this object plus H bar Jz plus J square Z. I can write this in terms of everyone else. Okay. So I can replace it with this fellow. I can choose to do that. Why do this? Because J square I know what J square is going to give me. I also know what Jz is going to do for me. Okay, so I know both of those, right? And this guy, by definition, this matrix element is also mod times that coefficient square times an inner product. But this, if this is a normalized state, that inner product is 1. So therefore, that's just this coefficient, which is what I want to know. Okay. So therefore, the coefficient square is just the action of this objects, J square minus Jz square minus H bar Jz. Okay. If you carry out the maths, you see that leads to this relation. This coefficient is just square root of J into J plus 1 minus Nj into Nj plus 1 H bar square. Yeah.
Could you explain 15.3?
Yeah, sure. So take that relation just above it, which is a definition. J plus acting on that state should give me the next state in the hierarchy with a coefficient. Now take its Hermitian conjugate. The Hermitian conjugate will give rise to the Hermitian conjugate of J plus acting on the bra. It has to, because the ket will become a bra, and the operator will also get its Hermitian conjugate.
J minus operates on
the bra.
Bra, but gives me C plus.
Yeah, because it's acting on the bra state. So if J plus was acting on the ket, if it gives me the coefficient, then J minus acting on the bra, which is J plus dagger, that will give me the same coefficient but star. Because the bra space will always give me the complex conjugates. So that's a natural outcome. Okay. So then I've just taken the product of these two. Okay, so I got a relationship for this coefficient. Except for you might have said once, that look, wait, this can't be the complete story. Because this coefficient, in principle, I got it out of a square root. Which means that there can be a plus minus sign. So there is a sign issue. Okay? So that's certainly there. Alright? But the sign issue is like choosing a phase, e to the I pi or e to the plus I 2 pi. These coefficients are never going to matter if I look at matrix elements, these phase factors. The rest, the amplitude will, the mod square will, but those phases won't. So that's why it doesn't really matter. So if we choose a convention, take the plus consistently or the minus consistently, it won't matter.
So,
Yeah?
so when you're writing J comma and one side of all the bra.
Yeah.
So I can't get it. That's why.
No, so the point is, good. It all boils down to this. Just this. Look at these two relations. Psi is such a state, this psi is basically equivalent to J and J. It is a state such that if I act on J square with it, it pulls out H bar square into J into J plus 1. So that piece of information is pulled out. And if Jz acts on that state, then what do I get? I get Nj into H bar. That's it. The exact mathematical form I'm not getting into. All I'm telling you is that these are the eigenvalues, these are the good quantum numbers, so therefore I can always write the state in terms of them. That's all. The explicit forms, yes, if we solve a differential equation like we did in the hydrogen atom, we'll see. There are some polynomials and some interesting things out there. We're not getting it.
This you said the space doesn't matter. You put a minus or a plus. Okay, you can just. So
In the mod square, it will never matter.
So is it the only reason we want to see the probability interpretation of that, or there is something else?
No, the probabilistic interpretation of quantum mechanics guarantees that. If I give you any state in general, I can always multiply it by a phase. That phase is arbitrary, but doesn't matter.
Is it the only reason we do this? We exclude the phase factor.
Yeah, pretty much. You can always choose to do your maths by keeping those phases around, such an arbitrary phase. It's just that at the end of the day, it will still keep hanging around and you'd never have gained anything out of it. So then you might as well wonder, like in any equation you write down, you can keep a lot of ones in product with everything. Do you do that? If you did, what would those ones lead to? Would they have led to anything? I mean, on some right hand side equal to left hand side, I can put in a 1 here and a 1 there, or a -1 here and a -1 there. Will it matter? Okay, so this is how we derive these relations of this kind. So the coefficients C plus, and you can also get a similar form for C minus, have these relations. Okay, so these relations might be of help, and if you know how to derive them, that's good. Otherwise, this is one of those brutal things of facts of life that you might just want to memorize. I usually don't give out this advice, but I find it useful. All right. So after all that stuff, we're now at last ready to get into spin. Okay? Spin angular momentum. So I'm skipping the hydrogen atom because you guys have all done it in the past. So there's no point reinventing the wheel. You with your beard seem very excited. That was really? Sorry? Yes. Fact of life. Come meet me in my office. I'll do it equally badly for you once more. No, seriously. I will not waste my time doing it a second time, because if I do that, then there are big parts of this syllabus which are going to just go down the tube. Can't do that. So I've given you my notes already, which have my version of the hydrogen atom in them, right? Have I not? You? Yeah. Read through it, and if you have doubts and worries, come meet me in my office. We'll revise it, okay? But I will not sit here and revise the hydrogen atom with you, okay? There's nothing gained from that. I mean, just imagine if somebody in a class keeps saying things like this. Yes, sir, but that was done very badly. Anybody can say that. Does that mean that we never make any progress in any of the courses? I mean, that's also partly your opinion, right? So, put in some hard work. Come meet me. I'll help you get through that. Now, you aren't even looking at me, my friend. How about I'm talking to you? How about you look at me? Yeah? So my message is to you and to all of you out there, if there is any particular part of the first course that you didn't really understand or got lost in the maths, come meet me. Right? We can go through it. It's not such a big deal. Right? Trust me, by the end of this semester, everything from that first course is going to look damn simple. Because that's the point. We're now going to discover much more complex stuff as we go along. Alright? So that's the entire point of all of this. I mean, things don't get any simpler as you go along, they only get harder. So let's get on with it. Okay, spin. Now, it's an experimentally observed fact that if you take something like a hydrogen atom and put it in an external magnetic field, funny things begin to happen. Okay? Those funny things actually led to a lot of the motivations for the discoveries of quantum mechanics. Just taking these atoms, putting them inside electric fields, magnetic fields, and watching what happens to the spectrum. Here, it turns out that what actually happens is that the system, that hydrogen atom problem itself, it actually acquires energy when you place it in a magnetic field, okay? Which means straight away that something in that original hydrogen atom is going to change. The Hamiltonian is going to change. But when you think about it, the hydrogen atom, which may have been taught to you very badly or whatever, but there was one special thing about the hydrogen atom which you must have appreciated, no matter how badly it was taught to you, which was that it must have seemed to you that the problem was delicately fine-tuned. Why? Because after all the hard yards you would have done to get to that final energy of the energy eigenvalue, you would have seen that it all depended on just one quantum number, the so-called principal quantum number. Whereas, while dragging you, kicking and screaming through the solution, you would have encountered the possibility of other quantum numbers. Right? What were they? The orbital quantum numbers. Then there was the so-called magnetic quantum number, which actually was spin, and so on and so forth, right? So all those guys were there. Yet, the energy didn't care about all of that. So what did that mean? Degeneracy. That according to that particular solution, which basically is what Bohr figured out way before people like Schrödinger actually did the dirty maths that you guys did, Bohr actually had figured it out. Okay, that's why he took home the Nobel Prize. But the point is that Bohr's answer suggests that all those so-called orbitals of the hydrogen atom are hugely degenerate. That's a pretty large degeneracy when you think about it. Why? Because there's L, the orbital angular momentum, Lz, M, Mz, all of those guys could potentially have started entering the game. They just don't. The chemists then turn up and tell you, yeah, you know, all of this makes so much sense. Why? Because the S wave orbital is just this one guy, but P has how many? Count carefully now. Don't do a bad job. How many states are there within the P orbitals? No, 6. Because in each of those P orbitals, I can put in 2 electrons. Sorry? Yeah, but there were some others who were saying 3, and their voice was much louder. Who was it? The smart Alex sitting at the back out there, no? You hiding behind the other guy. Yeah. No, but when you think about it, 6. That means all those 6 electrons sitting on those so-called 3p orbitals, they all have the same energy. Then what about if you go further? D. How many do we have there? 10. There are 5 d orbitals and times 2. Right? And it keeps growing. You go to F and so on and so forth, and it keeps getting worse. Even S actually has 2, space for 2 electrons. And those 2 electrons are degenerate in their energy. So this degeneracy, you might wonder how usually, I don't know whether the instructor of your first course pointed this out to you, but degeneracy is rather special. Nature hates degeneracies. Anytime a degeneracy turns up in nature, nature finds a way to lift that degeneracy. Okay? Degeneracy is extremely special. And yet, your solution of the hydrogen atom makes the huge claim that there are so many degenerate states. So then you might wonder, is this just an accident? I mean, nature is tolerating it for a reason, or is it that what we were shown there was just a fine-tuned version of the problem? And indeed, it's the latter. In your first course, God bless you, you were only showed that particular solution because that's all you could digest at that point. Reality is much more subtle. It turns out that all those degeneracies there all get lifted. But they're all lifted in very small, subtle amounts. So, if you're an experimentalist and you do the experiment not very carefully, you will think, oh, all these guys are degenerate. But then you start doing more careful experiments. And immediately those degeneracies start lifting. You know, you put the hydrogen atom in a magnetic field, and you see that even the S-wave orbital splits into 2. The P, how many will that split into? How many will that split? Just a simple magnetic field. Will it split into all 6 straight away? It will also split into 2 groups. And the D will also split into 2 groups. But the 2 P groups actually are hiding 3's inside them. And each of those 2 D groups are hiding 5's inside them. Okay? The S wave guy is just 1 in each. But this splitting into 2's is rather special. Okay? Why? Because of the following. The reason goes as follows. So if you really think about it, okay, maybe I have it here. Must be there. Okay. So if you think about using orbital angular momentum, all right, then how would such an angular momentum have responded to the magnetic field? The Hamiltonian is a scalar, energy. It has dimensions, but it's not a vector. So therefore, if you're going to play with vectors like magnetic field, there can't be too many ways in which it's going to enter into the Hamiltonian. Okay. The simplest way you could cook it up would be in scalar product or dot product with some other vector. Here, it turns out it's the angular momentum vector. Okay. So if you want to take the orbital angular momentum vector, okay, that's the orbital angular moment. Okay. You put this in product with the magnetic field. This could be one way in which that hydrogen atom, the electron, could start talking to the magnetic field. And then what is this moment? It's actually the Bohr magneton, mu b, which is EH bar by 2m. Okay. And I've divided it by h bar so that h bars would cancel. There's a factor called G of L that goes by the name of the Landé G factor, which here is just 1. Okay. For the orbital angular momentum problem, that factor is just 1. And then there's the L vector. Okay. So this L vector turning up there, all right, typically would give rise to, okay, if you think about it, if I'm sitting in an electron in the S equals to 0 state, sorry, the S wave state, what is the orbital angular momentum, the quantum number for L in that state? In that lower state, what is L in the hydrogen atom? 0. So then, could this electron in that state could it have talked to the magnetic field? Couldn't have, right? But indeed, it turns out, and that was the genius of Stern-Gerlach, they were playing with silver atoms, a mist of silver atoms, and in those silver atoms, the electrons was in an S wave state, not 1s. I think it was in 5s or something. That's right, 5s1. There's the chemistry. So, fair enough. And then, what do they see? They get a shock. They think this guy shouldn't talk to the magnetic field. But instead, they see that it does talk to the magnetic field. And what happens is that when they send in an atomic beam of these so-called 5s1 electrons, the electrons sitting in the outermost shell of the silver atoms, this beam actually splits into 2. Okay, so this magnetic field is generated, between these 2 magnets, and then this beam splits into 2. Okay, but 2. Wait a moment. This is L equals to 0. It shouldn't be splitting at all. So then what's happening? So then they realize, wait a moment. That means there must be some other source of angular momentum as well. Because if it was the orbital angular momentum, this beam wouldn't have split. Okay? So this itself is an extremely striking demonstration for the existence of spin. The Stern-Gerlach experiment. In a humorous historical aside, it turns out, and you can actually read about this, go look on it for the internet, that the discovery, as very often is the case, was accidental. They were trying to perform this experiment but not seeing anything. And then it turns out that Professor Stern, who happens to be an inveterate smoker, which means he's always smoking, he's a chain smoker, and cigars that too, he leans in pretty close to the apparatus and blows out the smoke into it. And then they see that these 2 things, stripes appear on the screen. And at first sight you think, Gerlach would have said, hey, what are you doing? You're screwing up my experiment. That's your dirty stuff on the thing. it turned out it was the silver atoms, and the smoke was necessary for some reason, which I've forgotten what. So that's one of those few examples where somebody doing something rather stupid in the laboratory actually led to one of the most amazing discoveries. So the next time you want to take a fag into the lab, and the instructor tells you, what the hell are you doing in here with that? You say, oh, I'm pretending to be Otto Stern. And of course, then they'll throw you out of the lab, but then you can walk out looking really cool. Right? And say, yeah. I mean, I find that thing extremely hilarious. I cannot imagine that something like that would have led to such an amazing discovery, but it's true. So once this experiment comes out, people realize that even the single unpaired electron sitting in that S-wave state, note, Srinivasa was very precise. He says 5s1. 1. What's that 1? What's 1? What's 1? It's a single electron sitting in that pattern. No, 5s1 means that all the other fellows are all paired up, which means that their net angular momentum is 0. So that's why 5s1 makes so much sense. This one guy, its orbital angular momentum should still be 0, so it should not have contributed, but that one fellow has some other property which is still giving you some angular momentum. This needed some time to understand, and it was Paul Dirac who figured out what it was, and that's a story that I unfortunately cannot really get into in any detail because it needs relativistic quantum mechanics to understand, and you need to see the maths. Okay, without seeing that maths you will not understand. But it turns out that that source of angular momentum has to do with the structure of the state space. The relativistic constraints, the constraints of special relativity on quantum mechanics forces the state space, the linear vector space, to change. And that change actually leads to this object we call spin. So this extra source of angular momentum. In a very strange, another historical aside, the people who gave the name spin to young graduate students working in Amsterdam or or Groningen maybe, they come up with an explanation for the Stern-Gerlach experiment. Uhlenbeck and Goldschmidt, very young, very bright young men. They go to their advisor, Ehrenfest, and tell him, look, we think we understand Stern-Gerlach at last. And their explanation actually visualizes the electron spinning on its axis. So they give their manuscript to Ehrenfest and they say, okay, why don't you communicate it? They ask their advisor to communicate it to the German. And, and then they forget about it. They go on to do something else. Meanwhile, Ehrenfest goes and has a discussion with Lorentz, the famous Lorentz, and points out that, these two young boys working with me have come up with this amazing explanation. Lorentz hears Ehrenfest out and says, Ehrenfest, there's a problem. Strictly speaking, on classical grounds, if you have an electron spinning like this, and if it's also talking to a magnetic field, it's going to radiate energy, and there are all kinds of issues associated with that, which quantum mechanics doesn't show us. Ehrenfest is now in a bind, because he doesn't have the heart to tell Lorentz, we've communicated that paper already. So they've already sent it off. Okay. And so Ehrenfest goes back and tells these two boys, guys, Lorentz pointed out that classically there's an issue with this explanation that you guys have. So the boys immediately tell him, give us back the manuscript, we're going to tear it out. He says, too late, I've already sent it off to the journal. So these guys are really worried now, thinking that their careers have ended. But Ehrenfest is a wiser man, and he says, look, don't worry, you're too young and you can afford to make at least one foolish mistake in your life. So paper gets published, and Goldschmidt and Uhlenbeck are credited with the explanation for spin. But we all know by now that it's actually Dirac who saves their behind by coming up with the proper understanding of spin. So these are some of the interesting stories of how all of this goes. But the last thing I want to tell you today is the fact that this object is the correct way to think about the Stern-Gerlach experiment. So instead of having a Hamiltonian that had the mu L talking to the B, you need to think of this object talking to the magnetic field as far as Srinivasa's 5s1 is concerned. Okay? This is the guy. So we're using the same idea. We say that look, instead of having L operator, let us pretend that there is some other operator out there called S operator, whatever this S is. And of course it has to have dimensions of angular momentum or whatever. So therefore I'll put in some mu B, the Bohr magneton, divided by h bar, and there will be a Lambda G factor for this time. So it turns out that the Lambda G factor experimentally observed for spin is actually 2.0023193, whereas quantum electrodynamics following Dirac, so Dirac's theory gives you GS.2, the Lambda factor is 2, but it turns out that all those corrections where you were wondering where is all this 0.0023193 coming from, it gets worse. It actually goes to 12, 13 decimal places. You need quantum electrodynamics to understand that. How the electron moving at the speed of light or very close to the speed of light talks to light. Okay, so it has to absorb radiation, give off radiation. Okay, those processes actually lead to these tiny modifications. You might think, what the hell, why should I care? Well, those small cares have actually revolutionized physics across the 20th century. So that's another story for another day. But okay, so that's what we do with the Stern-Gerlach experiment. From next class onwards, we're going to take this object, this spin operator, and we'll ask ourselves what its eigenstates look like, eigenvalues look like, etc., etc.